let's do a couple more examples of using the chain rule to find the derivative of function composition. So again, how to recognize, we always should have a function within another function. In this case, we have this whole thing to the fourth power, or this whole thing within a square root. And it's also it's important to remember that, let's say I have a ln of x squared, or the sine of x divided by 3x squared minus 9, or something like that. These would also be situations where I need the chain rule because I have an algebraic expression within another mathematical function. And we'll get more into ln's and logs and exponentials and stuff like that in a later chapter. And we're not actually going to cover trig functions in business calc. But in math calc, in general, the chain rule works in any context with any two functions whenever one is within the other. So let's do a few more. Again, key steps are take the derivative of the outside first. So the fourth power is what's on the outside. Keep the inside the same. So I can drop the power and subtract it by 1. And that's almost it. That's really easy. That's, how you might guess it would work if we didn't know any better. But the other key, the third step, which is another easy thing to forget, is whenever you're taking the derivative of something, when there's more than just x in the inside, you have to always multiply by the derivative of the inside. So here, the inside is it's a fraction, so I need to use the quotient rule still. So if you're like, well, then how do I take the derivative of this? You can't. Our other derivative rules still apply in the subparts of this rule. And since f of x is or g is the inside function as it's written in the chain rule, I need to take the derivative of this entire interior. So quotient rule. So I would need low d high minus high d low, square the bottom, and away we go. So these examples are notably more annoying because the amount of algebra needed is quite elaborate. But again, we should clean up our answers and make this look better as we progress. And actually, what you might notice is that actually the denominator ends up being the same. So the denominator is actually going to be totally cubed here. And this is not incredibly uncommon with such powers on rational functions like this. But the numerator is a little bit gross, for lack of a better word. So what I would do is I would simplify this right numerator, because this is a whole bunch of algebra that I could simplify, and then I would go from there. So I'll just go ahead and leave this alone, the first two parts. And since that whole fraction is cubed, I could actually rewrite this as the numerator cubed divided by the denominator cubed. And in the right case, by distributive property, this would give me 12x squared, and then I'm going to actually do minus 24x squared. So that's going to end up being negative 12x squared. I'm also going to have minus 66x. And I'm going to have 4 times 5 is plus 20. And all of that will be divided by 3x squared plus 5. And we could look to say factor this. Notice that there's a common factor of at least 4 within all of this. Actually, is 66 divided by 4? No, it's not. 2 is actually the only common factor. We could try to factor this, but at the end of the day, oops, I already forgot my squared. It's not always a necessity. Also, this 4 could multiply into this as well, or I could factor out 2. So there's a variety of things. I probably would just go ahead and factor out the 2, which would leave me with 8, multiplying into the numerator times 4x plus 11, quantity cubed. And this would leave me with negative 6x squared minus, I factored out 2, so this would be 33x plus 10. And the denominator, notice, is exactly the same. It was 3x squared plus 5 cubed times 3x squared plus 5 squared. So those are actually exactly the same. So those exponents will add 3x squared plus 5 to the 5th. And can I factor this? Whatever, maybe, but at this point, really, it's quite an ugly answer. Maybe I could factor it further, but that is good enough for now. And another question is, should I multiply this all out? I probably wouldn't. The original function wasn't multiplied out, so why should I do that to my answer? But, some online homework questions or some teachers might be a little bit more caring about how they answer it. This would probably not be a question I would put on a test just because of how horrible the algebra is, but it's good practice. And let's go ahead and do one more. Let's say I had this horrible rational function within a square root. Again, starting whenever I'm dealing with roots, it's helpful to think about them as exponents because I can transition it to be, I can transition to using the power rule instead. So I have this whole thing to the 1/2 power. And, in the same light, I could then use the extended power rule or the chain rule, again, which are really the same thing, but derivative of the outside comes first. So drop the power and subtract 1, which would be negative 1/2. And the other part is you can never forget, always multiply by the derivative of the inside. That is the importance of the chain rule. Here, the derivative of the inside, again, I would need low d high minus high d low. So I would have low d high, which is going to be 9x squared plus 5, minus high d low. And I need to square the bottom, and away we go. And that, again, is the chain rule. Take the derivative of the outside, leave the inside alone, multiply by the derivative of the inside. And I'll go ahead and leave this for you to simplify if you want. But again, pretty gross. There's a lot more I could do to make this look a little bit cleaner. But summary of the chain rule is if I have a function within another function, the derivative is never easy, especially when it involves division by functions, square roots, and so forth. It gets quite complicated, but it's nice to know there's always a simple underlying rule, the chain rule, which, if we remember our basics, can help progress through these sort of ugly examples.